All right, so in 1.1, we're going to talk about data, bar graphs, and pie charts. And so I'd like you to keep an eye on the objectives because as we kind of get into the lesson, it's easy to get lost in the content and forget, what are the important main ideas that I'm going to be assessed over. And that's kind of what the objectives tell us. So you want to be able to identify individuals and variables in a set of data, classify variables as categorical or quantitative, display categorical data with a bar graph and decide whether it would be appropriate to make a pie chart, and then identify what makes some graphs of categorical data deceptive. This is a fun visual pun that I should probably stop putting on there because students don't get it anymore, but that's a character from Star Trek The Next Generation, and his name was Data. So very good, always very funny to explain the joke. Here we go. So as you're taking notes here, I'm going to point out the things that you should be writing down in a composition book. Definitions are huge. These need to be written out. So we have 4 definitions here. First, individuals are the objects that are being described by a set of data. A variable is any characteristic of an individual. And that'll generally vary between the individuals. So there's 2 types of variables that this kind of branches out into. We have a categorical variable and a quantitative variable. So categorical variables places an individual into one of several groups or categories. A lot of times this isn't numerical. So if we're talking about human individuals here, one categorical variable could be hair color, right? So that differs from person to person, and it's not a quantity. A quantitative variable takes numerical values for which it makes sense to find an average. So if we're again talking about humans, this could be like height. All right. So do we ever use numbers to describe values of a categorical variable? And do we ever divide the distribution of a quantitative variable into categories? So the answer to both of those is going to be yes. I can give you a couple examples of categorical variables that we actually use numbers. So something like zip code, that just identifies the region that you're living in. It's numerical, but it doesn't really make sense to take the average zip code or even phone number, right? Same idea. Doesn't really make sense to talk about what the average phone number is. So these are both examples of categorical variables that are numerical. Okay, so when does it make sense to divide the distribution of a quantitative variable into categories? So let me think. So quantitative categories. So an easy one that's maybe familiar to you would be like grades. If you get a 94.7% in your statistics class, that means you are in the category of an A, right? If you get a 81.5%, that puts you in the category of a B minus, and so on. But there are lots of other examples when you are looking at a quantitative variable, but it is actually being divvied up into categories. So how much money a household makes, generally we'll put them in, lower, middle, upper class. So there's another example. All right, couple more definitions. A variable generally takes on many different values. We're interested in how often a variable takes on each value, and so a distribution is what tells us what the values of a variable takes and how often it takes those values. So That's our definition of distribution. So there are different ways of displaying a distribution. Here we're given a distribution of miles per gallon for different individuals. In this case, the individuals would be the model of car, right? So a table is just a raw layout of data. So it often doesn't, it's not a good visualization of a distribution. But our variable of interest is mile per gallon. And so one simple way to display a quantitative variable of interest is with a dot plot. And so we made one of these in the hiring discrimination activity. Oops. So there's a dot plot, and it just gives you a good visual. You can see sort of where the middle is, somewhere in here, right? So that might be a typical gas mileage for a typical car. You can see any outliers. So on the low end, we have some kind of car that gets 14 miles per gallon. On the high end, we have these hybrid cars probably that are getting like 33 miles per gallon. And so it's just a visual of the distribution of values. All right. So let's jump into an example. So here's information about 8 randomly selected US residents from the 2000 census. What are the individuals in this data set? So I said the individuals are the 8 randomly selected US residents. So next question, what variables are measured and identify each as categorical or quantitative? Well, in this case, each of the columns, I'll use red here, each of the columns is a different variable. And so I'm just going to label underneath the columns whether it's a category, or I'll do it above, whether it's categorical or quantitative. So state, that's categorical. Number of family members, that's quantitative. Age, quantitative. Gender, categorical. Marital status, categorical. Total income, quantitative, and then travel time to work, quantitative. All right. So this one asks us to display the distribution of gender and number of family members for individuals in the sample. So we're gonna choose how to display that. So we're gonna look at gender and number of family members. All right, so let's do gender first. This is a categorical variable. So what we're going to find out is that if you're trying to display a categorical variable, what you want to use generally is a bar chart. And I'll show you how a bar chart works. All right, so down here, I'm going to label this as gender. We're going to have male and female. And I need to go back and see, what did we have? We had 3 males and 5 females. So I'll add a scale. And so generally we'll just refer to this scale as the frequency. That's just how often each variable or each value of the variable occurs, the values being male and female in this case. So there were 3 male, so I'm just going to draw a bar up to 3, and there were 5 female, so I'll draw a separate bar up to 5. And there we go. There's how we can display the distribution of a categorical variable. Couple things that we're going to find. You need to be labeling everything as I did here. So make sure you label the X and Y axis. Make sure you also scale the Y axis in this case, the frequency axis, and that you label the values of your categorical variable, in this case, male and female, on the X axis. So the other one, number of family members, we can go ahead and use a dot plot to make that one. And so for that one, we just need a horizontal line. I'm going to label it number of family members so that we know what that x-axis is representing. And then I'm going to go, let's see, so we have anywhere between 1 to 6. So just start here and say, okay, 0, 1, 2, 3, 4, 5, 6. All right, and for each value, we want to put a dot above that value on our number line, and if there are repeats of that number, we'll just stack them up. So it looks like there's only one 1 and there's only one 2, so I can just go like that. We have 2 3s. I think 3 4s. And a 6. Perfect. So there's our two distributions that were asked for. First one is a bar chart. That's called a bar chart. Second one is a dot plot. So bar chart for categorical variables, dot plot for quantitative. All right, what's the difference between a data table, a frequency table, and a relative frequency table? When is it better to use relative frequency? All right, so to illustrate this, I have a couple tables. I don't have the raw data, but I have a frequency table and a relative frequency table. And this is, these are tables that represent the style of radio stations in the United States, right? So you can see the total number of radio stations is 13,838. A data table is when we are just looking at raw data. So in this case here, that would be like if I had a table that just listed out every single one of the 13,838 radio stations. So that would be a really big table, so I don't have that here. So the next thing we have is a frequency table. So a frequency table has now categorized some of your data for you by variable of interest. Okay, so now we've taken the 13,838 radio stations and we've broken them up into a variable of interest. In our case, the variable of interest would be format. So that's the style of radio station. So they're all put in a category. And then a relative frequency table is when you calculate by percent. So now you can see, instead of looking at whole numbers or frequency of radio stations, we're actually looking at what percent does each format take up in the market. And so generally you want to use relative frequency for comparison of multiple data sets when the raw numbers aren't the same. So what I'm saying is, like, if I wanted to compare the US radio stations with Canada radio stations, Canada probably has far fewer radio stations. They have a smaller population, right? So it wouldn't make sense to compare raw numbers there. But instead, what we would probably want to compare is the percent of the market that each format takes up in each country. So, you know, I don't know, maybe Canada likes rock music more, and let's pretend that their rock was 12% of the market. Then you could compare that with the US's 6.3, whereas just comparing the raw numbers wouldn't make sense because they have different numbers of total radio stations. All right. So frequency tables can still be difficult to read, and sometimes it's easier to analyze a distribution by displaying it with a bar graph or a pie chart. So again, this should actually, I would take points off on the test. This should be labeled frequency. You can also use a pie chart. In the pie chart, the angle of the slice of pie is proportional to the size or the percentage that category takes up of the whole. So you're never going to have to make pie charts or bar graphs by hand. I'm sorry, you are going to have to make bar graphs by hand. You're not going to have to make pie charts. And pie charts can be misleading and should only be used when you're talking about percentage of a whole. In this case, it's fine, but they can be misused quite a bit. Bar graphs are generally better. All right. So bar graphs compare several quantities by comparing the heights of bars to those that represent those quantities. Our eyes, however, react to the area of the bars as well as the height. That's why it's very important to make the bars equally wide when you make a bar graph. So you'll see this in like magazines, and when people try and make their data flashy, they'll use what's called a pictograph. And that's where you use pictures instead of bars. But because your eye is drawn to the area that the picture takes up, and when you enlarge that picture, the area enlarges disproportionately, it's a bad idea to use pictographs. All right, moving on. So in the 2008-2009 regular season, basketball player Dwayne Wade averaged 7.5 assists per game and 2.2 steals per game. Explain what's wrong with the following graph and how to make it better. So what's wrong is that they're using a circle instead of a bar. And as they okay, so I paused it so I could write this out, but I said the pictograph misleadingly makes it seem as if Wade had many more assists than steals, when in reality it was only a difference of 5.3. And so what I said is you should be using bars of equal width instead. So I can kind of draw that over it. So assists were 7.5, which should be about right there. And then steals right here. So the idea is because they're using the height of the basketball to represent the number of steals and assists he had, but as you increase a circle's radius, its area increases at a rate much more quickly, right? By a power of 2. Because area is pi r squared. So that area is increasing much more quickly than the height, which is misleading. All right, so a two-way table describes two categorical variables organizing accounts organizing counts according to a row variable and a column variable. So young adults by gender and chance of getting rich. So this is their opinion of their chance of getting rich. And so here there are two categorical variables. There's the opinion variable, and then there's the gender variable. Sorry. All right, the marginal distribution of one of the categorical variables in a two-way table counts is the distribution of values of that variable among all the individuals described in the table. That's kind of a word salad definition, meaning it's hard to make any sense of it. Here's what you need to know. The marginal distributions are the totals in the margin. So this is the marginal distribution for gender, and this is the marginal distribution for opinion, meaning opinion on getting rich. You can also do a two-way table and use percentages instead of counts. And again, they are often more informative, especially when comparing between groups of different sizes. So keep that in mind. All right, so we'll use the data. This is how to examine a marginal distribution. You can use the data in the table to calculate the marginal distribution in percents of the rows or the column totals, and then we can graph them to display the marginal distribution. So here they did the marginal distribution of opinion. Okay, conditional distribution. A conditional distribution of a variable describes the values of that variable among the individuals who have a specific value of another variable. All right, so how to compare conditional distributions. Select the rows or columns of interest. Use the data in the table to calculate the conditional distribution in percents of the rows or columns and make a graph to display the conditional distribution. In this case, we're going to use what's called either a side-by-side bar graph or a segmented bar graph to compare distributions. Great. So what we're going to compare is the conditional distribution of opinion based on gender. And so here's what that means. You're going to treat each gender as its own distribution. So I'm going to treat male as one distribution and female as a separate distribution. And I'm going to calculate a percent or a relative frequency within each category of opinion. So what percent of males thought they had almost no chance of getting rich by age 30? Well, we would do 98 out of the 2459, which comes out to 4%. And then likewise, I would do what percent of females said almost no chance of getting rich, and that's 96 out of 2367. Slightly different, 4.1%, right? And then so we go down each category, dividing the frequency by the total in their gender, and we get a percent for each. So if I added up all the female percentages, I should end up with 100%. If I add up all the male percentages, I should also end up with 100%. And I'll show you what a segmented bar graph looks like in a moment for that. All right, what does it mean for two variables to have an association? So I'm going to pause this and have you write out the definition. Okay, so two variables are associated if knowing the value of one helps predict the value of the other. And the graph of associated variables will look different across the distribution. So what I mean by that is gender associated with opinion of wealth or the opinion of your chance of getting rich by age 30? So they would be associated if their distributions across male and female were very different. Because then knowing the value of one helps to predict the value of the other. So these are pretty weakly associated. As we can see, almost the exact same in the almost no chance category between female and male. Slightly different in the some chance category. Many more females said some chance. Almost exactly the same in the 50-50 chance. Slightly larger percentage of male in thinking they have a good chance of being wealthy. And a pretty significantly larger percentage of males think they will almost certainly get wealthy. So I would say these variables are associated because if you're male, you're more likely to think that you will almost certainly get rich. But in other categories, they're almost the exact same distribution, right? And so what that means is when I make a side-by-side bar chart or a stack plot, which I'm going to show you, they're going to look pretty similar. If they were strongly associated, the graphs of those distributions would look pretty significantly different. But here's an example of a stacked bar chart. And so what you do with a stacked bar chart is each bar in the stack represents a different variable value. And so you're stacking it up to 100. There's no reason to have an order here other than whatever order you put these stacks in, you keep it the same between males and females so you can have comparison. So you can see that they are slightly different, like especially in these categories, in the green category. But they're not super different. So I would say this is a pretty weak association. A strong association, the stack plots would look much different. And so when we say association, again, it means is that knowing the value of one variable helps to predict the value of another. But that doesn't mean that one variable causes a change in the other. That just means they're associated with each other. Okay, and there's a big difference between association and causation. All right, so let's do one more example. The Pew Research Center asked a random sample of 2024 adult phone owners from the United States which type of cell phone they own, iPhone, Android, or other. Here are the results broken down by age category. All right, explain what it would mean if there was no association between age and cell phone type. Okay, so what I said is we would expect roughly the same conditional distributions across age. And then part B says, based on this data, can we conclude that there is an association between age and cell phone type and justify? So I'm going to start us out on this. What I'm going to do, I'm just going to extend our table. And so we're still going to have the 18 to 34 category, 35 to 54, and then 55 plus. But I'm going to create conditional distributions now. So I'm going to put percentages. So I'm treating each age group as its own data set. So the first thing I'm going to do for the 18 to 34, I want to know what percentage of that group use an iPhone. So to do that, we want to take the 169 and divide it into the 517. So in our calculator, 169 divided into 517, and that comes out to about 32.7%. Okay, and then I would just do the same thing I'm going to do for the Android now, 214 out of 517. That's about 41.4%. And then lastly, other, so that's the 134 out of 517. That's 25.9%. And I'm just going to do the same thing for the other category, or sorry, the other age groups. And so when you add, if I were to add that column up, it should be close to 100%. It probably won't be exactly 100 because I did round to the nearest tenth. So you could get some round off error. Okay, so I've finished computing my conditional distribution for each age category. And so based off this data, can we conclude that there's an association between age and cell phone justify? So I would say yes. There is an association between age and cell phone type. And the reason we know that, right, is the distributions are pretty different across age groups, right? Pretty predictably, in the 55 and up category, almost 3/4 of them use something other than an iPhone or an Android, which is probably something you would expect, right? They either have a landline or a flip phone or something like that. Versus in the 35 to 54 category, only 43% of them, 43.5% of them use something other than an iPhone or an Android. And in the 18 to 34, even more different, right? 25.9%. And so we just want to justify by saying, right, there are clear differences in the conditional distribution by age. Sorry, I did not space that very well, and you also can't see it because I have my window over it. There we go. So there are clear differences in the conditional distributions by age. All right, so that's our first lesson. Hope it went okay. Let me know if you have any questions.